So let's begin our session without any further ado. Let me just share my screen. So is my screen visible and I'm audible? Okay, yeah. Yeah. Thank you. Thank you. So, good evening, everyone. Welcome to the summary session for the course Colloids and Surfaces. So, this course is offered by Professor Basavraj from the Department of Chemical Engineering, IIT Madras. Myself, Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati, Assam, uh, who conducts live interaction session every week. So, in the last 8 weeks, of course, we have covered almost everything, and we also reached till our last live interaction session. So, just as a recap, I would like to you know, uh, kind of recollect what all we have discussed so far. So, starting from the very first lecture, we discussed on the concepts of colloids, what is a colloid, and we discussed on like the exact definition of a colloidal particle. After which we discussed about its classification. So I hope you guys are able to remember that. So based on the type of phase between the, I mean, based on the type of whether, so based on the type of dispersed phase as well as the dispersion medium, you have totally 8 different classifications. So the permutation combination between gas, liquid, and solid together gives you 8 combinations. I hope you are able to recollect. So you have aerosol, sol, emulsion, foam, solid sol. So and then the entire 8 different combination of dispersed phase and the dispersed medium. After which we discussed about the characterization of the colloidal particles. So over there we saw the concept of specific surface area, so which is nothing but the surface area of the particle divided by its mass. So anything, as I said in the previous interaction session also, anything which has the word specific prefix to it, you always need to divide that particular variable with mass. So this will, and this is universal, so you need to keep this in mind whenever this keeps coming. After which we discussed about a concept called surface charge density. So over there we discussed about the what is the difference between charge, a surface charge, and surface charge density. After which we discussed about the grafting density. So over there, if you remember, we kind of like went through how to calculate the grafting density, the experimental procedure for calculating the number of grafts present in the system. So I hope you are able to recollect about the TGA part, thermogravimetric analysis. And then we calculated the grafting density. Also, we saw why do we need to attach graphs to a colloidal particle, or what are the advantages of a graft. After that, we discussed on analyzing the size of the colloidal particle using dynamic light scattering techniques. Uh, so that concludes with the characterization of particles, beyond which we move towards the different type of forces. So can you name the 4 forces that usually acts in a colloidal system? Or are you able to recollect those 4 different type of forces? Any response? Yeah, one is your osmotic pressure, then Yes, then yeah. So those are the four different type of forces that usually act or that is usually under consideration for a colloidal system. So you have the hydrodynamic, Brownian, osmotic pressure, and after that you have gravitational force. So we also discussed the formulas. If you remember, what is for Brownian forces in terms of kBt, and for your gravitational force is nothing but 4 by 3 pi r cube times g times the difference between the density of the fluid and the density of the particles. Then for your hydrodynamic force, it is nothing but F is equal to 6 pi r eta v t. So like that, we discussed the different type of forces and its formulas. We further built up on the kind of interactions that is present inside the particles. So if you are able to recollect, we discussed about the depletion interaction, van der Waals interaction, hydrodynamic interaction, and in the van der Waals interaction, we discuss further in detail about the combination of that van der Waals forces of attraction. So if you remember, Debye interaction, Keystone interaction, and then at the end we move towards your London dispersion forces. So we also calculated how to uh, we also calculated this van der Waals forces of attraction as a sum of all these three different type of interactions within the van der Waals, that is your Debye, Keystone, and London dispersion forces. Further, we build on the depletion interactions, and then where we saw about depletion flocculation and depletion stabilization. So this was about the colloidal particles, their characteristics, and different type of interactions within them. Further to this, we added the concept of electrical double layer, which we are seeing for the past 2-3 weeks. So as I said in the last live interaction session, that was yesterday. So we have first the Helmholtz model. So then on that Helmholtz model, we incorporated certain, or that Helmholtz model has certain restrictions. So we further developed a model, or the scientists further developed a model without those restrictions, and they came up with the diffuse layer model. So in case of the diffuse layer model, the thermal motion of the molecules are taken under consideration. After that, further to this, there was a development where both the Helmholtz model and the diffusive layer model was combined. So for based on that, we saw how to calculate the surface potential equations for both your Helmholtz model, and then this diffusive layer model was given by the Goy-Chapman. So that particular equation we discussed. Further to this, we discussed about the interaction between the planar surfaces, and then we built up on the DLVO theory, where we discussed that the net interaction that is present between any two kind of surfaces, irrespective of their geometry, is nothing but it is the sum of the interaction energy due to the electrical double layer forces and then that of the van der Waals forces of attraction. So then in the last live interaction session, we further moved towards the concept of zeta potential, and we were solving some of the problems. So here is the question where we left yesterday due to some, I guess, time constraint. So this was a question. We were actually solving this. So let's continue solving this question and finish it off before we progress for the other questions based on contact angle and others. So here, so as I was explaining yesterday, so you have your value of kappa first for questions related to calculating zeta potential. you need to first calculate the value of kappa using this Debye-Huckel parameter. Sorry, using this equation, you calculate the Debye-Huckel parameter. So since the concentration is given in terms of mole per meter cube, you don't need to multiply the factor outside this sigma with 1,000. So if you don't do that, I mean, if you do that, so if you calculate this factor inside your sigma, so it comes Zi squared times Mi. Mi is nothing but the concentration of the electrolyte. So Z over here is nothing but it's a 1:1 symmetric electrolyte. So the value of Z plus as well as your Z minus is going to be 1. So which means, let me just write that. So this is nothing but 1 square times 5 plus minus 1 square times again your 5. So it's nothing but 5 plus 5, that is 10. So that's what is written here also, or I'll write 10 mole per meter cube. So that's what is given, 5 plus 5, which is nothing but 10. I hope you are able to see my cursor. So this one. And then we have estimated the value of Na E square by epsilon naught K T, where K is your Boltzmann's constant and T is the temperature. We calculated the value to be 5.405 into 10 to the power 50. This I have taken it from the previous problem which we have solved in the live interaction session. Since the dielectric constant is remaining same as 78.5. But please keep in mind that if your values are different, or please keep in mind that you better calculate this in the expression, the value of this expression every single time when you solve a problem, because the value of this will change based on your temperature and your epsilon, that is your dielectric constant. So since this value is subjected to change, because your dielectric constant is something which is like a parameter of the material, so it depends upon the medium which you are going to choose. So based on the medium, the value of the dielectric constant will vary. So it is always better to calculate it every single time whenever you see this kind of questions. So we have kappa square as 5.405 times 10 to the power 50 times this Zi square times Mi, that is 10. So if you multiply, it will be 5.405 into 10 to the power 16. So square root of this, just let me show. So 5.405 square root of this will be it is 2.32 into 2.32 times 10 power 8 meter power minus 1. So for kappa square it will be meter power minus 2. So kappa will be meter power minus 1. The RS, that is the radius or of your spherical particle, is 0.5 micrometers, because diameter is given as 1 micrometer. So radius will be half of that. So if you multiply kappa times rs, that is 2.32 times 10 power 8. So what is the value you're getting? Like, have you calculated this value? Or can you calculate this value and let me know? What is K times RS? Yes. What is the value of K times RS? Yeah. So that value is 116. So if you see here, so based on this value of K times RS, if it is less than 0.1 in dilute solutions or very low concentration of electrolyte, you are supposed to use the Huckel's equation. That is nothing but, as we discussed yesterday, it is 2 epsilon epsilon naught times your zeta potential divided by 3 times the viscosity. So yeah, here it is written. So U by E is called as your electrophoretic mobility, and epsilon is the zeta potential, and eta is the viscosity of the electrolyte solution that you are going to take under consideration. So here, yeah, so between these two regions, let's say if your KRS value comes between 0.1 to 100, then in that case, these two equations goes invalid. Over there, you are supposed to use Henry's equation. So I would, ask you to go through the video lectures by professor. In the video lecture named Electrophoretic Mobility and Zeta Potential Part 2, it is clearly explained about what to do if your concentration of the electrolyte solution is going to be between zero point 0.1 to 100. In that case, you are supposed to use the Henry's equation. So the Henry's equation goes something like this. So it will be given as f of alpha f of alpha is given as 3 by 2 minus 9 by 2 times alpha minus 75 by 2 times, let me just separate this with brackets, times your alpha power minus 2 minus 330 times alpha whole power minus 3. So this alpha is nothing but it is your KRS value. Alpha is KRS. I mean, sorry, K in the sense I meant kappa RS. So this should be greater than, if I it should be greater than 1. 1 or just a second. Yeah. So if in case of this, if your alpha, that KRS comes greater than 1, then you have to use this value, that is use this function f of alpha as this expression, 3 by 2 minus 9 by 2 alpha power minus 1 minus 75 by 2 times alpha power minus 2 minus 330 times alpha power minus 3. And then you need to substitute in this equation. Just let me use this. Times f of alpha. So this will be your expression, that is the generalized expression. So based on the value of f of alpha, you will substitute, or based on the value of alpha, you will calculate your f of alpha and then substitute in this equation and you can get the answer. So what you see here for KRS less than 0.1 and greater than 100 is nothing but after substituting the value in, actually this is one particular equation for KRS greater than 1. You have another equation where the value of KRS is less than 0.1. So that's the reason I asked you, it is better if you actually go through the video lecture. Over there both the expressions are given, you can use that. But for specialized cases where KRS is greater than 100, if you use this expression, all the, if you see it is here alpha power minus 1, right? So it will be 1 by 100. So that value will be very less. So you will be left out with f of alpha as 3 by 2. So if you substitute that here, this 3 by 2 and 2 by 3 will get cancelled and you will be ending up with this equation. So let me just show that as an example. So for alpha as 100, let's take for the example of 100, or alpha, any alpha greater than 100, your f of alpha is going to be equal to 3 by 2. So I hope you are able to understand why other terms are neglected, because if you substitute 9 by 2 times 1 by 100, or 100 to the whole power minus 1, so that will be 9 by 200. So let me write that. It will be 9 by 200 minus, it will be 75 by 20,000, and the other one will be minus 330 by 10 power 6. So these values the higher order terms will give very negligible values. So you can write this as approximately 3 by 2 itself, right? I mean, are you able to follow? Okay. So f of alpha comes out 3 by 2. If you substitute in this equation 1, what you will be getting is u by e will become, so this 3 by 2 will get cancelled with this 2 by 3, right? So you will be left out at the end with uh, or let me substitute and show, then it will be much clear. So now I am substituting alpha value as 3 by 2. 3 by 2, or better, so if you do this multiplication, then you will get u by e as nothing but epsilon naught times zeta potential by viscosity of the electrolyte. So you arrive at this equation, which is nothing but the Small-Chomsky's equation. So by from this Henry's equation only it is derived. So since here your KRS value is greater than is equal to 116, you can directly take this Small-Chomsky's equation. So I would better recommend, or like, it is better that if you remember these two expression with their condition, it will be helpful. That is u by e is 2 by 3 times of epsilon naught times zeta potential by eta for Huckel, and epsilon naught times zeta potential by viscosity for Small-Chomsky's equation with their respective condition. So this part is just for your what do you say, knowledge and information. So since here our value of KRS is 116, that is going to be greater than 100, you can use this equation to calculate your zeta potential. So what will be the value? So let me just write the expressions here. I mean, substitute the value. So your U by E, that is electrophoretic mobility, is going to be 4 times 10 power minus 8 meter square per volt second. So your U by E, that is electrophoretic mobility, is 4 times 10 power minus 8 meter square per volt second. Epsilon, that is your dielectric constant, is going to be 78.5. Epsilon naught is permittivity of the free space. So that is 8.85 times 10 to the power minus 12 Coulomb square per Newton meter square, and the viscosity is given as 0.001 Pascal second. So if you calculate, what is the value that you will get? 0.057. Okay, let's check. Let's calculate. Ten power 7 zeta potential. Okay, that's fine. We will just calculate and Let's see what is the value going to be. So it is going to be so this is nothing but 4 times 10 to the power minus 8 is nothing but it's equal to 78.5 times 8.85 times 10 to the power minus 12 times your zeta potential. So let me take this variable from here. This entire expression divided by your viscosity. So 0.001. So the value will be, so let's cancel the powers here. So this will be nothing but 10 power minus 3. So 10 power minus 3 is in the numerator and 10 power minus 12 is in the, sorry, is 10 power minus 12 is in the numerator and 10 power minus 3 is in the denominator. So if you cancel out, it will be 10 power minus 9 and this will be vanished. So you have 10 power minus 9 here, 10 power minus 8 here. So I can replace this as 4 and here I can make it as 10 power minus 1. So then your zeta potential value is nothing but 4 by 78.5 times 8.85, or you can write as 0.885. So this value will be 78. Let me just calculate the denominator first. 78.5 times 0.885 is 69.4725. So 4 divided by 69.4725 is 0.057 volt. 0.057 volt, or you can also express this as 57 millivolt. So this is the value of zeta potential. So you told something times 10 power. I mean, was there any issue? Okay, 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 fine. Then that's fine. So zeta potential value comes out around 57 millivolt. So similar questions are there for your assignment problems also. So please, I hope this will be useful for you to solve the assignment question. Do you have any like doubts regarding this question, or shall we move to the next one? Okay. So next question is about contact angle. Let me, yeah, read the question. So consider a spherical colloidal particle of 50 nanometer radius which is present at the oil water interface. The oil water interfacial tension is given as 80 millinewton per meter. So which is nothing but 80 into 10 power minus 3 Newton per meter. The contact angle at oil water interface is asked or is given as 120 degrees. They're asking you to calculate the surface area in contact or the surface area of the particle in contact with the water and the oil medium, the energy that is required to detach the particle from the interface to the water medium. So, how do you think should we solve this? So, my question is, when you have a contact angle of 120 degrees, so what can you comment about the nature of the particle? Any ideas? So, based on the value of your contact angle, is there is a possibility to comment about the nature of your particles in, or about the nature of your particle in a system? So usually, based on the contact angle, yeah, what I mean is the value of the contact angle, we can comment about the nature of your particle. So, for example, if you have a contact angle of less than 90 degrees, you have certain characteristics, or the particle will have certain characteristics. If it is greater than 90 degrees, it will have some other characteristics. And if it is 0 degree, if it is 180 degree, depending upon the value of the contact angle, you can classify the materials. So the classification is usually based on, or usually in a oil, sorry, in a water, and you can say air or oil. So in that particular system between water and oil or air, in that case, if your theta, or if the contact angle value is going to be less than 90 degrees, then you can call the particles as hydrophilic. If it is going to be greater than 90 degrees, then you can call that as hydrophobic. So if your contact angle is going to be 180 degrees, then you can call those kind of surfaces as super hydrophobic in nature. And if it is 0 degrees, you can call them as super hydrophilic in nature. So there are examples of particles, or you can say materials, which do exhibit what do you say, super hydrophobic and super hydrophilic nature in the literature and in the past, what do you say, yes, literature. So here we have to calculate. So here they are asking us to assume that the particle is going to be present in the oil water interface. They are asking us to calculate the surface area of that particle which is in contact with the water and oil medium, and the energy that is required to detach your particle from the interface to the water medium. So since the contact angle here, it is 120 degrees which is given. So for this kind of systems between water and oil interface and then the particle, you can call the particle to be hydrophobic. So which usually means that the more, what you can actually say is that more uh, surface area, or you can say a larger portion of the spherical particle or the colloidal particle is going to be present in the oil medium compared to water. So qualitatively you can say that larger area of the particle will be present in the oil medium compared to the water medium. But we need to quantify that. Again, how do you do that quantification? So we have equations. So for the surface area of the particle that is in contact with your water medium, you can give the expression, or the expression is given as APW, that is area of the particle in contact with your water medium, as 2 times pi 2 pi r square, just a second, 2 pi r square times 1 plus cos theta. So this is the expression for the area of the particle which is in contact with the water medium. Similarly, if you want to calculate what portion or what surface area of the spherical colloidal particle is going to be in contact with the oil medium, for that the expression is A OW, that, oh sorry, you can write it as APO. So that is area of the particle in contact with the oil medium. So the expression is going to be 2 pi r square times 1 minus cos theta. So these are the two expressions. So again, when you know your expressions, it just again, what do you say? Plug in the values and calculate. So let me just open my Jamboard so that I can show you the diagram. I hope this, just a second. Yeah. This Jamboard is visible. Okay, so as you, just a second. So take this as your planar interface. Again, when you have questions of this, it is a condition that your, or all these equations are derived for the interface which is planar or flat and undeformed in nature. So this is your interface. I can write here interface. So this is your interface, and here you have your oil, sorry, so here it is oil medium, and here it is your water. So your particle has a contact angle of 120 degrees, so it will be something like this. And then if you measure the contact angle, for measuring the contact angle, you need to draw a tangent at the point where your oil, water, and then the third interface meet each other. So this is going to be your theta, and the value of our theta is going to be 120 degrees. Just a second. This water, let me just write it down. This is going to be your water. So majority of the medium is going to be in the oil, or majority of the particle is going to be in the oil medium compared to water. So now, now I hope you will be able to calculate the expressions. What is APW and AOW? And for more explanation, I mean, if you want to have a clear diagram, you can see through the lectures. If you have any doubts also, please let me know based on what we have discussed regarding this contact angle or the previous problem. Yes, what is the answer? 1.57 into 10 to the power minus. Okay. Okay, let me also calculate. So it is 2 pi r square. So 2 times pi is 3.14 times r, that is nothing but 50 times, oh sorry, 10 to the power minus 9 whole square, 1 minus cos of 120 is minus 0.5. Oh sorry, APW is plus, right? So cos of 120. So cos of 120 is nothing but minus 0.5. So I'm going to replace this here itself. 1 minus 0.5. So let me give the multiplication sign. Yeah, it is 7.85 times 10 to the power minus 15. So previously was this thing is because of that square term with r. Okay. So again, you have it as r square because surface area is in terms of meter squares, right? So it's 2 pi r square times 1 plus cos theta for water and 1 minus cos theta for oil. Let me just calculate that. 2 times 3.14 times it will be 25 times 10 power minus 16. This times 0.5. 78.5 times 10 power minus 16. So that is 7.85 into 10 to the power minus 15 meter square. So similarly for APO, it will be 2 times 3.14 times 50 times 10 to the power minus 9 whole square times 1. Here it is minus cos theta. So that will be like 1 minus of minus 0.5. So you can write that as 1 plus 0.5. That value will be, what is the value? Minus 40. Yeah. So the value is 2 times 2.35 times 10 to the power minus 14 meter square. So this is PO, that is the particle which is going to be in contact with the oil. So this is your first expression. Of course, you have what do you say? One more term which is called as an AC. So AC is nothing but area occupied by the particle at the oil water interface when it is attached at the fluid interface. So when the particle is going to be at the oil water interface, what is the area occupied by it? So that is AC. So that we will not calculate, but I'll just give the expression here. It is pi r square I'll put this pi times r sine oh so that expression is AC, that is your AC is nothing but area occupied by the particle at the oil water interface when it is attached to the fluid interface. When it is attached at fluid interface. So this is the value of AC. So you can keep this in mind because sometimes I guess in your assignment there is a question where you are supposed to calculate the value of AC as well. So over there it is same. You just need to multiply whatever the values given and you'll be able to calculate that. Now, this is about the area of the particle which is in contact when it is in the contact. Suppose now I want to take the particle at the interface to one particular medium, or whether, or to be more specific, I want to detach the particle from the interface and then detach the particle from the interface to a particular medium, either oil or water. Then how much energy needs to be expend for doing this process, or for removing or for detaching the particle from the interface and then moving into one of the respective mediums? What is the amount of energy that will be required for this process? How do you calculate that? So that expression, I'll just write down, or delta G dW, that is the amount of energy that is required to detach the particle from the interface to the water medium, is given as pi r square times, you can call gamma O W, let me write this way, times 1 minus cos theta the whole square. This is the expression for the energy that will be required to detach your particle from the interface to the water medium. So here R again is the radius of the spherical particle or spherical colloidal particle that you are keeping under consideration. This gamma OW is nothing but is the interface oil water interfacial tension. Interfacial tension. So this is the surface tension that exists between the two mediums of oil and water, times 1 minus cos theta the whole square. Similarly, if suppose if you want to detach your particle at the fluid, or at the, yes, at the fluid interface, and then bring it to the oil medium, then that will be given as delta G dO is nothing but again pi r square times gamma O W, or the oil water interfacial tension, times 1 minus cos theta 1, sorry, 1 plus cos theta the whole square. So these are the these two is the, or these two are the expression for the energy that will be required to detach the particle from the interface to the water medium. Here your interfacial tension, if you see, is given out, is given to be 80 millinewton per meter. So this expression is nothing but 80 millinewton per meter. This is as per the question, as per given question. So what will be the amount of energy? So before that, if you see, if you see, as we said earlier, if you compare the area APW and AOW, you can see the values. APW, that is the area of the particle attached in the water interface, is, or in the water medium, is 7.85 times 10 to the power minus 15. But if you see that in case of APO, it is 2.35 times 10 power minus 14. So you can see there is a, if you make the order as same, it will be 2.35 and or 23.5 times 10 power minus 15, and that is only 7.85 times 10 power minus 15. So you can see that the particle, when you put it in the oil water interface at equilibrium, majority or the major portion of the particle is going to be in the oil medium. So it's more hydrophobic. It likes oil more, or it you can say more correctly as it does not like water. So it does not like water. So that is the reason the area that the particle occupies in the water medium is less compared to the oil medium. So similarly, you can see if you calculate both the energies, again, you can see the difference in their magnitude. So have you, do you have the values? What is delta G dW and what is delta G dO? Again, if your contact angle, yeah, go on. Yeah, and 413 times 10 to the power minus 15. What is the units? Yeah, joule. And your delta GDO, yeah, again joules. So you can see the difference in the energy also. If you see um, the amount of energy that is required in case of your delta G dW is more compared to delta G dO. It is much easier to, or it requires less energy to detach the particle from the interface to the oil medium compared to the energy that is required to detach the particle from the interface to the water medium, because the particle that you are what do you say, that you are going to place, or that you are uh, placing in the oil water medium is more hydrophobic, or it dislikes water more. So you can see the difference in the APO, APW, APO, as well as in delta GDW and delta GDO. So this is like, this is how you calculate the surface area and then of a particle if it is present at the interface, and then the energy. So does anybody have any doubts in this, either in calculation or in the concept? Similarly, if your contact angle is going to be 90, then in that case what happens is that condition is called neutral wetting, where exactly uh, where you can say the area that will be present in case of water as well as the oil medium will be the same, because it's going to be exactly present in between your oil and water. There will be no excess portion in the oil medium in case of hydrophobic surface, or excess portion in water medium in case of hydrophilic particles. And that is the reason it's called neutral wetting, because it has no, what do you say, difference in the way it wets the surface so of the particles. So can we progress to the next question, or is there something that... Okay. So, okay, just before that, let me just write the entire expression, because power minus 3, because it's in millinewtons, times 1 minus cos 120. So similarly, it will be 1 plus. So that I hope everybody will be able to do. So let's move on to our question number 3. So this is something which is similar, is the same as your week 6 assignment problem. So then, since this question is slightly different from what we have seen in all the live interaction sessions, so I would like to discuss this once again. So you'll be getting the, what do you say, a written solution, just like how you got for the 5-week lectures. You'll be getting it within a day or two for week 7 and week 6 and 7, and then once the deadline for week 8 is over, you'll be getting for week 8 as well. So the question number 3 states that surfactant molecules in solution form micelles above a particular concentration called critical micelle concentration. The number of surfactant molecules in a single micelle is also termed as aggregation number. Again, so as they are going to form micelle, that means more surfactant molecules are going to get attached to form one single micelle, and the number of the surfactant molecules, since many are going to get aggregated, it's called as the aggregation number n. So we conduct a particular experiment where the radius of the sodium dodecyl sulfate, it's also called SDS, it's a surfactant. So it's something, this SDS is very commonly and more, and you can say a very popular surfactants which is actually used specifically in the field of material science, especially in polymers. We use this SDS quite often to form for multiple purposes. So here the radius of the sodium dodecyl sulfate micelles is found to be 22.1 into 10 power minus 8 centimeter, and they have obtained this value by light scattering experiment. They It is written that in order to measure the zeta potential at dispersion of this micelle in 0.01 molar NaCl is considered. It is also found that the zeta potential is 92.3 millivolt. They have given the surface charge can be approximated as 4 pi epsilon naught times zeta potential times R times 1 plus k kappa R. Useful quantities are given. They are asking you to, it's a step by step calculation. First, they are asking you to calculate the value of kappa, then surface charge, then surface charge density, then number of charge groups in the molecule, and then they are asking you to calculate the aggregation number, provided that the 20% of the molecules on the surface of the micelle are going to be dissociated. So this question is same. So I hope you will be able to tell me the answer for A and B, because we have solved that quite a number of times as assignment problems during live interaction session also. So what is the value of kappa and Q, as well as I mean surface charge and surface charge density? So please keep this in mind, since the concentration here is given in terms of molar, which is nothing but moles per liter. To that, to this expression, you need to multiply it with Na, that is your Avogadro number, times 1000. So what is the value of kappa, surface charge and surface charge density? Yeah. So kappa value is let me just write the entire expression. So meanwhile, please let me know the answers for Q and Q. I mean, sorry, surface charge and surface charge density as well. So this is your expression for the Debye-Huckel parameter calculation, and so here, as I said previously, since you have the NaCl in molar, you have to multiply by 1000. So again, since it's NaCl, Z will be plus 1 plus 1. Sorry, plus 1 and minus 1. So I'm not going to write that step here. Instead, I'm going to just write 0.01 plus 0.01. So that is going to be 0.02 molar. So my value of kappa square comes out around, just a second. It comes out around 1.08 times 10 power 17 meter power minus 2. So the value of kappa is going to be, let me just change everything. So your value of kappa is going to be root of this. So that comes around 3.28 times 10 power 8 meter power minus 1. So this is the value of kappa. So once you know kappa for surface charge, you have the equation given in the question. That is Q is nothing but 4 pi epsilon naught times zeta potential R times 1 plus kappa times R. So you can use that. So let me keep this here. Here you just need to substitute every value that you have in this expression. If you do that, you will be getting 4 times. Let me substitute. Meanwhile, you can calculate. Epsilon dielectric constant 78.4 times 8.85 times 10 power minus 12 times zeta potential, that is given as 92.3 millivolt. So 92.3 times 10 power minus 3 times, you have R is given as the radius of the sodium dodecyl sulfate molecules. R is found to be 22.1 in times 10 power minus 8 centimeters. So you just need to convert that into meters. So it will be 22.1 times 10 power minus 10 meters. We are converting that centimeter to meter times 1 plus kappa times R. So kappa comes out around 3.28, 22.1, and then the powers 10 power 8 and 10 power minus 10. So you'll be left out with 10 power minus 2. So I'm going to write here that as 3.28 times 0.221. I hope it is clear. So what is this value going to be or coming out as? So I have calculated this expression previously. So please let me know whether it is correct. 3.006 times 10 to the power minus 18 coulombs. Is there, please check your, this with your answer and tell me whether it is okay. So your surface charge density is nothing but, let us move to a next slide. So surface charge density is nothing but we have solved this multiple times. So what is surface charge density? It is surface charge by what is the denominator? It's a ratio of two quantities, or it's like by area. So surface charge density is nothing but surface charge by area. So you have calculated your surface charge to be how much? Let me just check once. 3.066 times 10 power minus 18 coulombs. So let's use this expression. 3.066 times 10 power minus 18 by 4 pi r square. So 4 times 3.14 times r square. R is 22.1 times 10 power minus 8 centimeter. We are writing it as, since it's r square, I'm going to write it as 22.1 times 22.1 times 10 power minus 20. So you have r square. So r is 22.1 times 10 power minus 8 centimeter. I'm converting that to meters. So it will be 22.1 times 10 power minus 10 meters. Since it's r square, I'm going to write that exponent part as 10 power minus 20. So if you do the simplification, then your surface charge density will come out as 0.05, sorry, 0.05 coulomb per meter square. In fact, let me show the calculation here. So the expression without the numerator, just a second, there is some error here. Let me tell the value. So this will be nothing but 3.066 times 4 into 3.14 times 22.1 times 22.1. So that is 6134.4296. This entire expression times 10 power or times 10 square, because 10 power minus 18 in numerator, 10 power minus 20 in denominator. So it will be 10 power, what do you say, 10 square in the numerator. So if you do this value, you will be having, if you do the multiplication, you'll be getting 0.0499 coulomb per meter square, which I am writing it as approximately equal to 0.05 coulomb per meter square. So are there any difference with what you have calculated? Okay. So first three parts is easy. Now the third part is, or you can say the part C, number of charged groups in that molecule. How will you calculate the number of charged groups? Since this is an assignment question, I hope you would have previously solved, but for those people who still have some confusion, how do you solve for the number of charged groups in the molecule? So the Q that you obtain is the total amount of charge that is present in the, you can say, the micelle, the total amount, the total charge in the micelle. Now you want to calculate for one molecule how many charge groups are present. How do you calculate the number of charged groups? So any thoughts, any ideas on calculating number of charged groups? So can you write it like this? Q, that is your surface charge, is equal to N times E, where N is nothing but is the number of charge groups, and E is the, what is called, charge carried by one electron. So if you remember in the very first live interaction session, we solved a problem where we were asked to calculate the surface charge density. Over there, we were given with a molecule which has a base charge 2. So the charge that is going to be present is 2. So in terms of coulombs, the value was 2 charge groups times 1.6 into 10 power minus 19. So similar is what you have here also. So can we write this? So the total number of charge, or the total charge in the molecule by the charge of one electron will give the number of charged groups. So Q value, you know, that is 3.066 times 10 power minus 18 is equal to the number of charge groups times 1.6 times 10 power minus 90. Can we write it like this? Any confusion or any like? Can we write it this way? Q equals to N times E. N is the number of charge groups and E is the value of, what do you say? One, you can say it as the electronic charge in one group, or yeah, the electronic charge carried by one group or one uh, molecule. So if you just divide now, you will be able to calculate the number of charge groups. And that's simple division. So any like you are unable to understand how did we come up with Q equals NE or yes, 19.19 I believe. Just flip. Oh, oh, it's 30.66 by 1.6. 19.16. So approximately roughly you can say 20 charged groups, or yeah, 20 charged groups in one molecule, because the charge that is carried by one group is 1.6 times 10 power minus 90. You have so much amount of charge in the surface or in the micelle. You know the charge of one particular group, that is 1.6 times 10 power minus 19. You are just asked to calculate how many groups are present in the micelle or in the molecule. You know the charge, like what is the value of one charge group in a molecule, or it is nothing but the electronic or the charge of one electron. From there you can calculate the value of N. So this is about calculating the number of charged groups. You have another one expression, another one question, sorry. Calculate the aggregation number N if 20 percentage of the surface molecules are dissociated. So 20% of the molecules are on the surface of the micelles are dissociated. Now, if that is the case, what will be the aggregation number, or you can say how many surfactant molecules are going to be present in one single micelle? How do you calculate that? Any ideas on how to calculate aggregation number? So for calculating aggregation number, you don't have any specific formula, unlike other case. So if you see this question, you don't have any what do you say, specific or special formula. It's just that once you calculate the value of kappa, you can easily calculate the other three parts of this question. So you just need to concentrate in question D, you just need to concentrate on the second part of the question. If 20% molecule on the surface of the micelle are dissociated, why is that information given in that question? So it is simple. It because that 20% of the molecule, or you can say that 20% of the dissociated molecules are only responsible for the surface charge that you calculated. The surface charge you have written, we have calculated as 3.066 times 10 power minus 18, right? So this surface charge comes from only the molecules that are dissociated from the surface of the micelle. So for example, let's take one particular functional group. Let's keep it as COOH. So this is one of the surface groups. But this group will not have any charge, no net charge. Only when this dissociates, it will have some charge as COO. Uh, just a second. It will have COO minus. So now only it will have one negative charge on its surface. So whatever the charge that you have calculated comes because of this dissociated molecules, and that is 20% of the whole micelle. So I guess I have given the answer. Now you will be able to calculate what is the aggregation number, or in simpler terms you can say number of surfactant molecules in the micelle. So number of charge groups is 19.16. So this 19.16 is nothing but the 20% of the dissociated molecules from the surface of the micelle. So if 20% of the something is 19.16, what is the total number? You can say if 20% of the entire system is going to be 19.16, then how much is the or what is the value of that system? 95 point. Yeah. So as I said, it is 20% of N, or you can say number of surfactant molecules is equal to the number of charged groups. Again, this is as per the question. So that is nothing but 19.16. So 20% of something is 19 point something. So 19.16. So number of surfactant molecule in the micelle, in a single micelle, or you can say aggregation number, or you can say n is equal to 19.16 times, sorry, 1 minute, times 100 by 20. So that is 19.16 times 5, which is 95.8. Yeah. So approximately you can say the aggregation number is 96. So here it's just that what I want to emphasize is that only the surface charge groups that are dissociated will show charge. Like the COOH is a surface group, but it will not show any net charge. But when it gets dissociated, it will have a -1 charge on its surface, and that's what contributes to the total charge on the entire surface of the micelle. So for the micelle or for any colloidal particle to show charge, the surface group or the charge group should be dissociated. So that is something that I want to emphasize. Do you have any doubts, or shall we progress for one more question? Yeah. So again, this is also very simple one. This is your week 8 practice question. So it states that optical microscopy was used to measure the electrophoretic mobility in a dilute aqueous suspension containing 1.84 micrometer diameter amide in latex particle. Okay, it's 1.84 micrometers. Zeta potential versus pH is given. Concentration of the monovalent chemical species, that is nothing but your electrolyte solution, was adjusted, is used to adjust the pH, and its concentration is 10 power minus 4 molar. Epsilon naught, epsilon r value is given. Q expression is given. Rs is the radius of surface particle, and elementary charge is given. They are asking us to calculate, identify the pH above which the particles are negatively charged. Okay. Then they are asking us to identify the isoelectric point from the plot. Further, they are asking us to calculate the surface charge and estimate the surface charge density. So part A is easy. So for the particles to be negatively charged, which means its zeta potential is negative. So if you have to determine what is the pH, it is simple. You just need to draw a line at 0 zeta potential. Just a second. Oh. So yeah, you can take this. Oh, yeah. So you draw a horizontal line at zeta potential equals to 0, and from here you drop a vertical line. So it's just about using the graphs to calculate the value. So if you see here, I think it will be somewhere around, if you draw properly and check, it will be somewhere around 11.4 or 11.5. So this is simple. So pH of of either 11.3 or 11.4, or you can say 11 point, yeah, 4 to 11.5. So this is the pH above which means greater than 11.4, 11.5, like 12, 14, the zeta potential, or you can say the particles are going to be negatively charged. Then they are asking us to calculate the isoelectric point from the plot. So what do you mean by isoelectric point? Any ideas on what is isoelectric point? Isoelectric point. So, isoelectric point is nothing but it is the point at which your zeta potential is going to have a value of 0. That is, the point where your zeta potential is 0 is called as an isoelectric point. So from here you can say that at a pH of 11 to 11.3, the isoelectric point is, or at a pH of 11 to 11.3, zeta potential is 0. So that is the isoelectric point. But what is more important is to understand what is exactly the use of this isoelectric point. So isoelectric point is something that is of more importance in case of, the field of proteins. People who work on drug design and this protein engineering, they usually deal more, or you know deal frequently with this concept of isoelectric point. Usually this is used in case of drug design, like you can say any kind of medicinal drugs that is used. This isoelectric point is useful because based on this isoelectric point, they will, tune the interaction between the enzymes and then the target receptors. So based on this isoelectric point only, the people, or you can say the scientists, develop different drugs for different medications, and also it is used in protein purification. So usually when you have, or when you want to purify a protein structure, so for that case this isoelectric point is usually used. It's also called isoelectric focusing. So over there what they do is they take a gel matrix, and then to this gel matrix they will apply a pH gradient, and then electric field is applied. So due to the application of the electric field, what happens is one end of your gel matrix is going to be positively charged, and then the other is going to be negatively charged. Now here what they do is they apply, or they send in the protein. So because of this pH gradient and the electric gradient, the proteins which have different charges move towards the positively charged part of the gel and the negatively charged part of the gel. At one point what happens is the isoelectric point comes out to be 0. So at that point the protein gets precipitated out. So this isoelectric point is used for protein purification, and especially very important when the proteins have very close, what do you say, you can say for protein purification purpose this isoelectric point is used. Again, if you are interested, you are welcome to, you know search for more about how this isoelectric point is used in protein purification purpose. Then what is the protein purification purpose process? It's a beautiful process, so you are welcome to explore. So this question is at pH of 11.3 to 11.4, sorry, to 11.4 to 11.4. Zeta potential is 0. Hence the isoelectric point. Now, part C. Calculate the surface charge Q at pH 11. They have given the zeta potential value is 20 millivolt. So, it's just substituting in this expression. Once you substitute, you will get the value, and C and D part is something very similar to what we did here. We calculated Q from this expression, and once we get the surface charge, we just divided that with area to calculate the surface charge density. So here they have given the zeta potential value to you, that is at pH 11 the zeta potential is 20 millivolt, and from there they are asking you to calculate the surface charge. Once you calculate the surface charge, you have what do you say, radius of the particle as 1.84 micrometers. So it just Q is nothing but 4 pi r square. Let me just give that. Q star is nothing but Q by 4 Q by 4 times 4 pi r square. So this is the surface charge density calculation, and for surface charge you just need to substitute the values in this expression. I'm not sure what. So epsilon naught. So once you substitute it here, you'll be able to get the surface charge, and from there surface charge density. So since we are running short of time, we have one question here. So I think you will be knowing how to solve this. So anyway, let me just give hints for this question. So for calculating the electric field strength E, we have discussed the formulas previously also. I guess if I'm not wrong, it will be sometime during week 5. So you can always go through that slide. It's already uploaded in the Google Slides. Uh, for like you can access it through the problem solving session, that Google Slides. So I'll just give the formulas here. So it is Q by 4 times 4 pi epsilon naught times r square. Just a second, let me make it more clear. So this is your electric field strength, or strength of the electric field. So again, here just I want to mention surface charge density is given. So as I said, it is nothing but Q by 4 pi r square. So now you can calculate E as nothing but surface charge density, that is your Q star by epsilon naught. So you don't need to know what is the value of R if you have the surface charge density value with you. So now it's just about, you have surface charge density as 6.9 times 10 power minus 2, and you have the relative permittivity as 80, and permittivity of free space is given as 8.85 times 10 power minus 12 coulomb square per Newton meter square, or coulomb square per joule meter. Once you know the value of E, they are asking the potential drop. So you can write E is nothing but delta times psi by delta x. So delta x is nothing but it is going to be the thickness of your double layer. So once you know the value of E, you will get to know the value of delta psi, or the potential drop. And your what do you say, delta x is going to be the thickness of the double layer, that is 4.4 times 10 power minus 9 meters, and your E value is around 9.7 times 10 to the power 7 volt per meter. Please be careful with the units. So if you multiply, you will be able to calculate the potential uh, drop. So I will upload this PPT with the values in it. So uh, do you have any doubts related to what we have discussed in these two questions? Hmm. I mean, you are asking me the pattern. Hello? Okay, so pattern will be mostly, it will be similar to what you what you have solved during the assignment problems. If you see, you have multiple choice questions with all that what do you say, with those definition type. Then you will have match the following, and then you might also have the numerical type answers where you have to type the values. So the pattern will be very similar to what you do for your assignments, or what you have done for your assignments. Okay. Yes. Meter cube, you don't need to multiply that 1000. But this mole per meter cube, you, in the question, if you see in assignment questions also, all your assignment questions have it as molar, right? It is given as 0.01 molar, 0.001 molar. So in all those cases, it is 1000 times Na, that is your Avogadro number, times E square, that is your electronic charge square, by epsilon naught At times sigma Zi square Mi. Okay. So do you have any other doubts? I mean, in general, anybody else have any doubts? Let me just stop presenting. If you have any doubts, I'll be available for some more time. You can ask. Since this is the last live interaction session, yes, please. Okay, 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 okay. So let me conclude the session. All the presentations and the YouTube videos will be available to you very shortly. So I thank all of you for joining all the live interaction session for almost we had 9 live interaction sessions so far. I thank everyone for taking their time and joining the session. I hope it was useful for you. I would like to thank Professor Basavraj as well as the NPTEL team for providing me this opportunity to interact with you all every Sunday from 5 p.m. to 7 p.m. So, if you have any doubts, please feel free to email me. My email will be available in the presentation. I will return to you as soon as possible, or if you can also use the Q&A forum that will be available to you. So, thank you everyone, and all the best for your exam. So, I hope to meet all of you in some other course in the future. Till then, bye and take care.